solved to a certain extent, all right, or rather minimized, by having a large number of general purpose registers, which can be used as temporary storage, all right, before they're actually written to main memory. Okay. So essentially, you would store interim values in the general purpose registers before you actually write them to main memory. Okay. The next element that causes pipeline stalls, or the most common element that causes pipeline stalls, is that known as data dependencies. Essentially, data dependencies are when you have instructions which depend on other instructions that you're currently executing. Now, as I said in our previous lecture, sometimes reordering the way that those instructions are executed, all right, may solve this problem and therefore reduce the amount of storage. However, this is predominantly down to the efficiency of the compiler, the compiler that is converting the program that we need, all right, into instructions that can actually be executed by the CPU. And there are three different kinds of data dependencies, all right, that we need to know. Okay, notice that, guys, this topic is one of the more important topics and is usually asked within examinations. So it's a good idea to know these quite well. All right. So you have the first situation being the read after write. All right, also known as the raw data dependency. In which case we have a situation where we have one instruction, all right, that needs to refer to a result that has not been calculated or retrieved as of yet. All right. This is because, again, the instruction that is being executed is being executed exactly after the previous instruction, where the previous instruction needs to perform one of these operations. And we can see an example over here. Okay. So over here we have R1. So the data within R1 and the data within R3, all right? When I say R1 and R3, we're talking about registers, all right? So the data within register 1 and the data within register 3 need to be added together, and they need to be saved within registered 2. Notice that the next instruction over here, okay, have certain codes that mean certain things for the computer to do, and you're able to convert basically what those commands into ones and zeros that the computer can understand. Essentially, you've created a programming language. However, not every programming language is as efficient as others. It's the same thing with pretty much everything that we have in our world. Not every car is as efficient as the other. But they might work better in certain circumstances.
Yeah.
Okay. So that's the second situation. The third situation is the write after write data hazard. Essentially, the write after write data hazard is going to manifest itself when there is some form of delay to the write back function, all right? In this case of instruction 2, all right? If there is a delay, essentially, in this case, you would want, again, this is because of concurrent implementation, you would want that the write back into register 2, all right, for instruction 2 would be delayed, all right, until the write back of instruction 1 has been carried out, for two reasons, all right. First, in this case, the first instruction is basically saying, I'm going to update register 2 with the data within register 2 added with the data within register 1. If register 2 is somehow updated, all right, before this execution, all right, then essentially what we're going to get is a false value within register 2. Okay, so we need to make sure that when we are writing to the same location, essentially, with this register 2, in this particular example, that we sort of wait until the first instruction has completed before we can actually continue with our write back function ourselves. Okay? Any questions up to this point?
I'm fine, thank you.
Okay. All right. The third type of situation that can generate these pipeline stalls is what is known as controls transfer. Essentially, control transfer is a situation, all right, within code, all right, whereby you have jumps or branching or loops, all right. These kinds of operations in a piece of code, all right, can in fact, all right, produce what is known as a control transfer. Essentially, if we think about it, all right, if we think about a normal algorithm, or a very basic algorithm rather, the implementation of each and every step, all right, within our code is done one step after the other, all right. So first you do the first step, then you do the second step, then you do the third step, and so on and so forth. However, in more complicated algorithms and more complicated programs, you might have situations whereby you need to decide what you're going to do based upon some form of value. All right? So you're going to be doing a decision. If, for example, this value is equal to 5, then I'm going to do this. If this value is equal to 6, then I'm going to be doing the other. All right? So that is what is known as a branch. All right? So you have a branching structure within your code. Similarly, you could also have a situation whereby you're executing this algorithm, and at one point it will tell you, okay, if you reach this point, then jump to instruction number 600 and disregard the rest. And that is known as a jump call. All right. Or a situation whereby you're going to be continually repeating the same piece of code over and over and over again in a form of loop. All right. These are all different kinds of control transfers that can actually occur within a programming language. Now, whoops. So, how do we avoid these control transfer stalls within our pipeline? So one way that we can go about it is by inlining. All right. So essentially, whenever you have a jump call, all right, to do another execution of the code, what you would do is you would reorder the code. You say, all right, I'm going to take these instructions which exist down here, and I'm going to place them right in line where I actually need them to continue, so that my instructions, all right, are followed one after the other, essentially. Another way of doing this with regards to loops, for example, is to roll them out. A loop essentially is a piece of um, repeated code, all right, that is done for a number of different times. So what you would do is you would literally repeat the instructions, all right, obviously making sure that you're updating certain values as you're going along in order to make the code more linear, all right. When it comes to branching, on the other hand, all right, so deciding whether or not you're going to go down one line of execution or another, all right, what the CPU would usually do is it will guess which one or which line of execution is actually going to be followed. If the line of execution that was guessed is correctly guessed, essentially, then there's no problem. Essentially, what you would have done is you would have one over certain certain a certain amount of time for the CPU, because essentially you would have guessed correctly. However, if you've guessed incorrectly, then essentially those instructions, even if they are partially carried out, that shouldn't have actually been carried out, those would be disregarded, and you would continue from the next instruction that you would need to execute, essentially. So, let me give you an example. So let's say that if let's come up with a simple execution, all right, or a simple branching statement. If it is raining, then I will take an umbrella. Otherwise, I will just take a jacket. All right, for example. Okay, so if it is raining, I will take an umbrella. Otherwise, I'll take a jacket. Okay. So what your CPU might do is it might assume, for example, that your if statement, all right, or your branching statement is always going to be true, for example. All right. So therefore, it will assume that you're going to take an umbrella, and it will continue executing the line of taking the umbrella, if you understand what I mean. However, if at some point at the if once the execution of the check whether or not it is raining or not, all right, every if statement comes with sort of like a condition, all right, once the condition has finished executing, and therefore now you know which line of execution you need to go down to. If that happens to be false, essentially it will stop all of the instructions that it has partially partially executed, disregard them, all right, and start continuing on the other line of execution. Is this clear to you guys?
Yeah, sure. From my end.
Okay. So essentially, this idea of predictive branching essentially is a way of how to speculate what the execution is going to be without having to flush the pipeline each and every time. However, sometimes you're going to speculate incorrectly, and therefore you will have to flush the pipeline at that particular point in time. Okay. Now, obviously, nowadays we are working more and more with CPUs which have what are known as superscalar architectures, i.e., a CPU with multiple execution units and therefore multiple pipelines. All right. Now, this might mean that these different CPUs might have multiple ALUs, all right, or multiple floating point units, all right, which are similar to the arithmetic logical units, all right, which can obviously take into consideration calculations having to do with floating point values, all right, but essentially these multiple instructions, all right, need to be executed simultaneously, and therefore you would need to try to keep each and every pipeline for each and every execution unit or each and every core working as efficiently as possible. All right. So essentially, with such architecture, you're going to average more than one instruction completed per clock cycle. All right. Obviously, the more cores you have, the more the more probability you actually have in creating multiple in calculating multiple instructions per clock cycle. All right, because obviously you'll have multiple pipelines, all right, and depending on the number of pipelines you have, all right, or the number of threads that you can actually execute at any given point in time, you're going to have a number of instructions completed at the same time. All right, not necessarily equal. All right, because obviously you might come across pipeline stalls in each and every one of those pipelines that we mentioned. Okay. Yes. Yes. So essentially, a clock cycle is well, first and foremost, it is a trigger, if you will, of a certain circuit within the CPU. Okay. Essentially, different CPUs have different clock speeds. All right. If you look at your computers, all right, or the CPUs, or all right, even within your assignments, all right, in the previous principles of computer architecture course, you were looking at computers or laptops. Excuse me, with different CPU speeds. All right, so you had CPUs with, for example, 3.4 gigahertz. You know, what does that mean? It means that essentially, if you have 3.4 gigahertz, that means that you have 3.4 billion in cycles. All right, or switches that you can turn on and off per second. Okay, that's what a clock cycle is. Now, obviously, different CPUs have different clock speeds. All right, as in they can turn on and turn off these switches faster. Okay, Therefore, if you have a higher clock speed, then your clock cycle, all right, turning on and turning off a particular circuit within your CPU will take less time. Does that answer your question? Um, memory doesn't usually make use doesn't usually have the same speed as the CPU. All right. In fact, memory tends to be slower than the CPU. If you take a look at a typical computer store, so let's uh, just for completeness sake, all right, and we'll look at I don't know a laptop. Okay, any laptop will do. Okay, choose this one. Okay. Um, uh, if we take a look at the specs, all right, you can see over here that your CPU speed is 1.1 gigahertz. All right. Um, but the RAM, all right, might be actually a bit slower. This won't doesn't actually tell you. Um, uh, Probably gaming laptops have this information a bit better. Yes. So.
Are we comparing frequencies here between the RAM and?
Yes.
Mhm.
So usually,
Yeah.
if you look at DDR
DDR4
for
starts from 1600, I believe, or 1333 DDR4.
so here's the clock rate um, of starting from. All right, the cheapest, to starting from 1600 megahertz or 1.6 gigahertz to a certain extent. All right. Um, uh, Obviously, if your CPU is faster, all right, then you can only access it as fast as the RAM allows you to. Okay. Um, uh, Obviously, it is different hardware specifications might mean that you would have different different bottlenecks or potential bottlenecks within your RAM. All right. One way that you would also sort of like you would overcome this. All right, is by having larger caches. So the cache would be a piece of memory which is associated with the CPU. All right, which works at the same rate as the CPU. All right, which is sort of like a buffer between the CPU and main memory. And you might also have multiple levels of cache, really and truly, because the more concurrent execution you actually have, um, uh, the more it's probable that certain pieces of information are not actually going to be stored in cache. But we're going to be talking about cache in a later topic um, um, in this course. So for the time being, I would like we'll keep that as an aside. What I wanted to point out is that usually when it comes to speeds, all right, the CPU and the CPU registers are usually at the same speed of the CPU itself, all right. Whereas main memory is slightly slower, but obviously a lot bigger, all right, in terms of capacity. All right, if you remember even that diagram that we had seen, all right, usually you'd have the larger the larger the capacity, the slower the access time. Usually, okay. Not necessarily, not necessarily. You could have instructions which might require more than one step. If you think about it, it's kind of like a clock cycle is as the most basic operation that you can actually is the amount of time for the most basic operation that you can actually execute. All right. Even say, for instance, in I don't know, say cooking, for example. All right. If you are trying to perform an operation, all right, when you're cooking, all right, I don't know, chopping, all right, a single slice might be a clock cycle, if you know what I mean, of an ingredient. However, if you want to mince it finer, then you probably need more than one operation, and that would be the overall operation that you're trying to execute, if you know what I mean. Yes. We're actually going to be discussing this a lot more. So if you allow me, I'll get to it and we'll be able to understand. So in the most in the most basic and in the most ideal situation, all right, each clock cycle will allow you to perform a function within the pipeline, right? So you'll have one clock cycle, for example, to fetch an instruction, one clock cycle to decode the instruction, one clock cycle to read inputs, and so on and so forth, okay? However, every time we are performing a function within the pipeline, at some point we will then need to transfer the execution, if you will, of that particular instruction to the next stage. So essentially, if I am fetching an instruction, okay, all well and good. I have managed to fetch an instruction. However, I now need to hand over to the next stage, all right, certain data, all right, in order to be able to perform the decode cycle, all right, and so on and so forth. But this handing over of data, all right, or handing over of procedural context, if you will, all right, is something that takes some time, all right, and it's inevitable, all right. If you are sort of like think of it in terms of a factory, if you will. In a factory, all right, we said that yes, at each point, all right, we could be doing something particular within the pipeline, if you will, of the manufacture of that particular product. However, there is also the production line, meaning that when you've formulated one stage of that product, you then need to transfer it to the next stage, and that transfer, even if it is small, also takes time. All right. So last time we came up with the example of a bottling factory. All right. So if you were filling up a bottle, all right, after you fill up the bottle, then you would need to screw on the cap. But between filling up the bottle and screwing on the cap, there's obviously going to be a small fraction of time before you can actually perform the next operation. All right. The same thing happens in the stages of the pipeline. In fact, between each stage within the pipeline, there exists what is known as a pipeline latch. Essentially, you're latching the performance of this particular stage with the next stage. You're linking them together. That's why it's known as a pipeline latch. All right. Now, essentially, when this pipeline latch is executing, all right, or is happening, the CPU is not really doing anything, all right. Therefore, the greater the pipeline latch, all right, is in relation to the number of in relation to the actual execution of the code, the less efficient your CPU is actually going to be. What do I mean by this? All right. So let's take a little bit of an example. So let's say that we have a processor, all right, which is unpipelined. Okay, and let's say that in order to execute an instruction, we need 25 nanoseconds. All right, so we have 5 stages. All right, these 5 stages, we have fetch, instruction, decode, read inputs, compute, and write result. All right, and between one instruction between um, one process and the next, there's always going to be this pipeline latch. All right, so if we take 25 nanoseconds and evenly divide them up for each clock cycle, then essentially we're saying that each stage is going to take 5 nanoseconds in order to compute. All right, let's then say that each pipeline latch, all right, takes 1 nanosecond. So 1 nanosecond of latency, of time that is of execution that the CPU is never going to recover from, essentially, because it's wasted. Then essentially, all right, what we can say is that each cycle, each clock cycle, is going to be 5. So the actual number of nanoseconds that you're going to have, all right, in order to execute that particular stage, plus 1 being your pipeline latch, meaning it's going to take 6 nanoseconds in order to execute and then transfer to the next stage. Okay, so in this case, all right, your latency time is going to be 1/6 of the overall time, all right, that you have on your CPU. So essentially, 1/6 of your execution time on your CPU is going to be wasted. All right. You might say, but what if I have more stages? All right. Say a 50-stage pipeline. All right, and it also takes 25 nanoseconds in order to execute a particular instruction. Then essentially, what we're saying is that each stage will take 25 all over 50 nanoseconds in order to compute. But if the latency time of the pipeline latch is still 1 nanosecond, all right, therefore taking 1.5 nanoseconds per clock cycle, the amount of latency in this case is 2/3 of the overall computation time. All right, so this proves, all right, over here, that having more stages within the pipeline does not necessarily mean that your CPU is actually going to run faster. Is this understood? Sometimes it's better to have less stages within your pipeline rather than have more, right? Because at one point the amount of latency that you have between one stage and the next would be very, very, very significant, all right, in terms of your overall computational power. Does this
Okay,
make
so
sense?
sir, just to be clear from this,
Yes.
so if you increase the stages within a pipeline,
Mhm.
you reduce the latch latency, but since it adds up over.
No. The latch latency remains the same in this case because you still have to. If it in this case we're saying assume that the latch latency is always going to be the same. all right, is going to be of 1 nanosecond. Okay, as in that is the amount of time that it actually takes in order to go from one stage to the next.
Okay, all right.
Alright.
So what is actually the value within
Mana.
25 divided by 50, for example?
So that's 0.5. 0.5 plus 1 is 1.5.
But how is that value attained? What
Mana.
is the logic
Mana.
behind it?
So essentially, what we're talking about here is the ratio, all right, between the pipeline latch latency, all right, versus the actual execution time required for each stage within the pipeline.
All right, okay.
Okay. If you have a lot of stages within your pipeline, all right, but you're going to keep the same amount of time in order to for those stages to be completed, all right, but your latency time remains the same, then essentially what that means that even though your clock cycle is shorter, all right, the amount of time that is used within your clock cycle, which also has latency, all right, is going to be far more present than if you had less stages within your pipeline. Does that make sense?
Because it adds up over time.
It's basically
Sort of.
no. So the idea here is I can either have clock cycles which are shorter, all right, but if I have clock cycles which are shorter, but my latency time between one stage and the next remains the same, all right, then my CPU is going to be down or is not going to be as efficient as possible. In fact, in this particular case, 2/3 of the time for each clock cycle is going to be wasted doing absolutely nothing. Essentially,
I understand. Okay.
moving from one stage to the next. But you're not
Okay, alright.
really executing the instruction, if you know what I mean, because
Mhm.
these stages are the execution cycles, if you know what I mean. All right.
Alright, so basically, if the latency stays the same, and you increase the stages within a pipeline, that will that will
imagine you're trying to cook, all right, something which is very complicated. All right, Valentine's Day is coming up. You might be tempted to do something of the sort. All right, if that were the case, all right, probably, if I had to tell you, okay, you need to chop these ingredients, then you need to prepare these other ingredients in this way, then you need to prepare those other ingredients in this other way, and so on and so forth. If I give you an amount of time which is substantial, all right, in one stage versus in one portion of need of your cook, all right. So if I give you 5 minutes of chopping versus 5 minutes of sautéing, for example, and 5 minutes of plating, you would probably be more efficient than if I just gave you 1 second of each. All right? Because between you moving from one stage to the next, that's going to take time. That's what I'm trying to say.
I understand. I visualized it from my end, and then I was able to understand what you are saying better here.
Okay. Are there any other questions with regards to this, guys? Did everybody understand it?
So and so, I'm okay with the maths. Okay, yes, if we divide.
Essentially, what I'm trying to say is, if I what what this is like, all right, is imagine you have a list of tasks that you need to do which are completely separate from one another. Okay? If I give you more time to execute each task individually, you're probably going to be more productive than if I had to tell you, okay, do these same tasks, but in shorter spurts, all right? And then you have to sort of like context switch between one and the next, all right? In a very similar way, the CPU with regards to the CPU, sometimes it makes sense to keep each sort of like process or each stage within the pipeline sort of like larger, so that you have more time dedicated to the execution rather than switching from one context to the next.
Exactly. So it's a question of limiting the latching time.
Exactly.
All right.
Or the proportion of the latching time
Exactly.
per clock cycle.
That
Yes.
looks like
Yes. Yes, that's
so it
the
makes
idea.
more sense to lengthen the processing as opposed to switching from one stage to another and then
Exactly,
losing
because
the
switching from one stage to another is inevitably going to have some form of latency, i.e., where your CPU is absolutely doing nothing.
result.
All
You're
right.
actually using it instead of.
Exactly. 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 All right.
Thank you.
Essentially, what you would do is, instead of splitting, if you split down each sub process into finer and finer stages, the more obviously pipeline latches you're actually going to have. All right. It might be simpler in terms of its overall architecture. All right, but it might be the case that is not going to be as efficient as it needs to be. No, for CPUs, what you would have is, for any CPU, all right, the goal is to not waste a lot of time, sort of like switching from one context to the next. All right, you want to execute instructions as fast as possible. All right. Again, it's not necessarily going to be the case that your pipeline latch is going to be constant. In this case, it's constant in order to make it easier for us to understand. All right. So there's an element of balance, essentially. All right. Sometimes you cannot always state that you're going to have an adverse reaction. However, um, if you have too many stages, all right, it might introduce. It might make the CPU architecture simpler, but it might introduce more latency time. All right. On the other hand, if you have too few pipeline stages, then probably it means that each CPU cycle or each clock cycle is actually going to be much longer, and any stall that you might have within your pipeline is going to be more significant. Do you understand? So it cuts both ways. Sometimes you need to find a balance. Okay? All right. Okay, so here's a question, all right? So, in order to again delve a bit more deeper into the same ideology. So, let's suppose that you are asked to design a processor, all right, which has 5 stages, all right? In this case, the 5 stages that we have, okay, have different completion times. This is more realistic to what we were talking up to this point. So let's say that it takes 20 nanoseconds to fetch an instruction, it takes 10 nanoseconds to decode an instruction, it takes 20 nanoseconds to execute that instruction, 35 nanoseconds in order to perform any form of memory operation, and 10 nanoseconds in order to write back. Okay? So notice we have now different stages which take different amounts of time. Okay? So what can happen is the following. You can look at the minimum clock period, which can make our processor function. Now, this can be done in different ways. Okay, you could look at these and say, all right, which is the clock cycle which is going to allow me to perform each and every one of these instructions? What would you say? What is the clock cycle length that is going to allow me to execute each and every one of these each and every one of these pipeline stages? 35. So essentially, if I take a clock cycle of 35, all right, then essentially we're going to be able to execute all of these instructions. However, over here I'm going to have 15 nanoseconds sort of like waiting around in order to move on to the next stage. Over here I'm going to have another 25 nanoseconds waiting around. Over here I'm going to have another 15. All right, over here I'm going to have 0, and over here I'm going to have another 25. So essentially what we're saying here, all right, if we take a little bit of a calculator so that we understand what's going on. All right, so we'll have 15 plus 25 plus 15 plus 25. We'll have 80 nanoseconds, sort of like wasted, if you will, all right, in order to move from one instruction to the next. Because if a clock cycle, all right, is going to be of 35 nanoseconds in order to incorporate this this larger process, if you will, then essentially what we're saying is that we're going to be waiting this amount of nanoseconds per instruction, all right, because these different operations take less time. Does this make sense?
Can you can you repeat that, please?
So, if we have a clock, if we have a clock cycle of 35 nanoseconds, yes, and let's say we're executing this stage of the fetching of the instruction.
Mm-hmm.
If we take only 20 nanoseconds, how many time is left?
It's 15.
15
So
nanoseconds.
in total, what you're saying here, that in total, after executing all of these with a 35 nanosecond clock cycle, you would have wasted 80.
You do have wasted 80, all right? And if we had in total, which is essentially, if we had to calculate it in terms of a percentage, okay, it's 45% of the of the execution is wasted.
Mm-hmm.
You know, so
Yeah.
that is significant, essentially. All right.
But
So what you yes,
if I may ask, but
yes,
between one clock and another, the highest time of wasted time is 25 nanoseconds, right?
in this case, yes.
Okay. Because they will be like executed one after each other because there are other groups going on.
Exactly, because one instruction, in order to execute one instruction, you first have to fetch it, then you have to decode it, then you have to execute it, then you know. But even if I finish earlier, all right,
I have to wait for the.
I have to wait for the next
seconds.
stage. Exactly. Okay, that's essentially the
So
idea.
the longest time is 25 seconds waiting, 25 nanoseconds waiting.
Or for a particular stage, yes.
Okay.
In this case, all right. So obviously, we can sort of like look at it at how we can actually improve the performance. Okay. Another question that you might be asked is if you had to redesign the same CPU, all right? In this case, having 50 pipeline stages. Is it going to be 10 times faster than one which has 5 stages? All right? And this would be a probable answer. So, as we were saying, the minimum clock cycle that encapsulates each and every stage is going to be that of 35 nanoseconds. However, having faster or having more pipeline cycles or pipeline stages doesn't necessarily make it faster. All right, it's very unlikely that it's going to be faster because the larger the amount of pipeline cycles or pipeline stages, the more chance you're going to have of hazards and stores. All right, so it doesn't necessarily mean that it's actually going to be any faster. So how can we actually make this CPU better? All right. So what we could do is instead of having pipeline stages, all right, which are equal to the largest size of, or the largest stage, if you will, what you would do is you would find a pipeline stage which is as short as one of the shortest stages. So let's take another example. In this case, let's say that we have a CPU which has 4 stages within its pipeline. So stage 1 takes 30 nanoseconds, which is fetching the instruction. Stage 2 takes 9 nanoseconds, which is decoding the instruction. Stage 3 takes 20 nanoseconds, and stage 4 takes 10 nanoseconds. All right. In this case, what we can do is we can come up with maybe an asynchronous time for the completion of a single stage within that pipeline. How do we do that? Well, if we again look at this instruction, you can see that altogether it's going to take you 49 nanoseconds to complete. Why? Because you have 30 plus 9, so that's 39, plus another 30 for stage 3 and stage 4. That's 69 nanoseconds. All right? The longest stage is 30 nanoseconds. If we had to create a processor which had to take 30 nanoseconds per stage, it's actually going to take longer because you have 30 times 4, which is 120 nanoseconds. Right? However, what we could do is we say, all right, what is the smallest stage within our pipeline? In this case, it's 9 nanoseconds. We also have another stage which is 10 nanoseconds long. So what we could do is we can say, all right, the first stage, we can divide our clock cycle in terms of units of 10 nanoseconds each. The first stage will take 3 units of this pipeline stage. The next stage will only take 1. The next stage will only take 2, and the stage will only take 1 again. In this case, all right, we have 7 stages or 7 units times 10 nanoseconds, which means it's going to take 70 nanoseconds in order to execute rather than 120 nanoseconds. In this case, it means that your CPU, all right, is going to be much more efficient, all right, in executing your instructions if the CPU clock speed was of 10 nanoseconds rather than 30. Does this make sense, guys?
Yes, it makes sense from me, but does the result factor in the pipe latches that we are having in between?
Yes. I'm assuming that they're included.
And the pipe latch, it's only between one stage and another, not between one clock cycle and another.
Essentially, the clock cycle is inclusive of the latch.
Oh, okay. So it includes.
It includes the latch.
All right. So you would have, just to visualize this, for example, for the first stage, you would have three clock
blocks
cycles,
used
and
up,
then one
followed by
latch.
one. But the 3 clock cycles also includes the latch.
It also includes the latch. All right, inside it.
All right.
Inside it. Okay.
That was sort of like an apart. So essentially, what we were talking about earlier is that each clock cycle is going to include a portion of execution plus a latch.
Okay.
That's what I was trying to allude to earlier. But then having too many latches or having too many stages might increase the amount of latches that you're going to have, therefore the amount of latency.
All right.
All right.
Understood. Okay. Thank you.
But in this case, what I'm trying to point forward is that even if you have unequal pipeline stages, all right, in terms of duration, the amount of computation per stage is actually different. You could go in either direction. You might just say, all right, which is the largest one, and I'm going to stick with that particular clock cycle in order to accommodate that. However, you're going to have obviously an amount of wastage, all right? Versus saying, all right, which is the smallest one that I can sort of like use as a clock cycle, and I would just use multiples of in those stages which require more computing time, essentially. Obviously, the pipeline is going to be a bit more complicated in order to make as efficient, but in essence, each instruction is going to take less time in order to execute. Do you understand this point, guys?
Yeah. From my end, I understand. Yes.
Everybody else okay? That's the memory. This memory operation. It's short for the memory operation. So memory. Okay. All right. Right. The next sort of like subtopic that I would like to talk about is mentioning, all right, the different type of instruction sets that a CPU could actually belong to. All right, a CPU can be known as being a CISC CPU, or it could also be known as a RISC CPU. Have you ever heard about this term?
No.
No.
Nope.
Okay.
No.
So, what does this mean? So, a CISC CPU basically means a complex instruction set computer. Okay? What does this mean? It means that the CPU will have a large number of instructions that it can execute very quickly by flicking on a switch within the CPU itself. All right? Obviously, having many of these instructions inbuilt into the CPU, sort of like hardwired, so that you can literally turn on a switch and compute that particular instruction, means that it is going to be very, very hard in order to design the overall architecture of that CPU. All right, and therefore the design of the CPU is going to be very, very complex. All right. However, a complex instruction set computer, all right, or a CISC computer, is a CPU that mirrors very much so the structure of higher level programming languages that we use when coding. All right. However, so obviously this comes with a certain element of benefits. All right. Essentially, usually when you come up with when you have a computer which has a complex instruction set, it means that the translation from the high-level language into machine code, all right, the ones and zeros that the computer actually understands, is relatively simple, all right, because there are sort of like 1:1 relationships or close to 1:1 relationships between structures that are used in code, all right, that can be represented represented in the instruction set that the computer can actually execute. However, if you have instructions which are very, very simple, all right, then the then it could mean that it would take actually longer in order to execute simple instructions than it is in order to execute larger instructions. All right. Essentially, there's going to be a lot of resultant code. All right. For each instruction that needs to be executed, because each instruction is more expressive. All right. What do I mean by this? If I had an instruction that would be able to, I don't know, perform some highly complicated mathematical construct like differentiation or integration, which is sort of like hard coded within your CPU. All right, then probably the translation is actually going to be simpler. However, if you're then going to try to perform a basic addition, for example, the instruction needs to be pretty much as long as the other instructions that you might have had. All right, which obviously means that the code or the machine code that is going to be used for the control unit in order to understand what it needs to do might be more complicated, all right, especially for simpler instructions. In fact, whenever you are converting from the high level language into machine code, most of these types of CPUs make use of what is known as microcode. Microcode is essentially it is taking the application itself and breaking it down into instructions that it can carry out in individual chunks on its own. All right, the CPU can execute on its own, and then executing it in that particular order. Think of it in the sense that I have a particular set of procedures that I need to do. All right, and I have these tools. So essentially, what you're going to do is you're going to break down these tasks so that you will be able to use these tools in order to carry them out. Okay, so it's kind of like saying, if I have a toolbox, all right, which has a lot of different types of tools within it, all right, then probably I would be able to do a lot more than if I had a number of simple tools, all right, basic tools. But what I would need to do is I would need to organize myself in such a way so that I know which tool I'm going to be using at any given point in time in order to carry out the instruction that I had in the first place. Does this make sense to you guys?
It does. In short, a CISC is a bit of an overkill when it comes to simple instructions, then.
To a certain extent,
To a
yes.
certain extent, unless
To
you
a
might
certain.
code it to compensate for it.
In fact, there are alternatives, as you're going to be seeing in a moment.
Okay. What I didn't get was how is it simple for high-level language to be translated to well binary? To low level?
Because the complex instruction set CPU has a number of sort of like hardwired operations that can literally just be called, and they tend to match the instructions that are given in high level languages.
Okay.
That's
Alright,
why.
so-
So there's a more 1:1 relationship, if you know what I mean.
So by design, it's meant to have the tools necessary for certain complex instructions delivered in
Yes.
high-level language.
Yes.
Alright, so it's not because of the chunking, because the third point was because high-level language, of course, it's more direct, it's more closer to our language, and so it's
With more complicated instructions.
yes.
But then with simpler instructions, then you're going to have even a simple instruction is going to be bloated, if you know what I mean.
Yes.
That's essentially what we're
Yeah,
talking
too many
about.
layers then for just a simple instruction.
Yes, it's kind of like saying,
You know,
if I have
using a V8 for like a 1 kilometer commute,
excuse me.
like using a V8 for a 1 kilometer commute, like a high
For
power.
example, yes. It's overkill for something simple.
Exactly.
So making use of a piece of equipment which is overkill. If I had to saw a piece of wood this big, it would be overkill if I took a chainsaw to it. I mean, a
Yes.
simple saw would be sufficient. That's essentially what we're talking about here. Okay. Yes. 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 Obviously, that would mean that they're more expensive. And it might not necessarily be um as efficient. Then again, it depends on how you're going to be using it. All right. In fact, if you take a look at the disadvantages of a CISC CPU, mainly it's speed, because you first need to convert it into sort of like microcode and then convert it into machine code. All right. Optimization. All right. As well as pipelining. All of these all of these elements tends to take a bit of a nosedive, all right, in terms of performance. However, on the other side of the fence, you have what are known as RISC computers, or reduced instruction set computers. Essentially, a RISC CPU is very small by design and has a very simple instruction set. All right. Which basically means that the instruction set is designed in order to be as regular or orthogonal, all right, as possible, all right. Essentially, when it comes to these instruction sets, the main advantage or the main focus here is on efficiency, in order to be able to pipeline as much as possible, in order to be able to have superscalar designs, all right, and faster register reads and writes, all right, and faster execution. However, all right, with regards to risk instruction sets, if you have complicated instructions, what you would then need to do is you would need to break down those complicated instructions into these very simple instructions, which means that you might bloat the amount of instructions, all right, that you would need to execute in order to execute a simple larger instruction, which would be easily executed using a complex instruction set computer. So essentially, over here, what we have is, if you're talking about a complex instruction set computer, you're talking about an architecture which can handle very complex instructions very easily, but really can't handle simple instructions as easily. All right, and on the other hand, the reduced instruction set computer can handle very simple instructions very, very quickly and very efficiently. However, when it comes to complex instructions, then you end up bloating the amount of work that you would need to do in that case. All right. Ideally, you would have something which works in the middle. All right. In fact, there exists. All right. Um, um, there exists hybrid systems. All right, which are an alternative to a RISC or a CISC CPU. In fact, most modern CPU designs have elements of both RISC instruction sets and CISC instruction sets. All right. In fact, what they also make use of is what is known as the long instruction word architecture, where each instruction, all right, is made up of a number of RISC-like instructions, but they are executed by different parts of the CPU, essentially. All right. Usually, this would in turn rely. The efficiency of this would in turn rely on the compiler's ability to be able to carry out these long instruction words um, uh, in such a manner that you'd make best use um, uh, of your CPU. There also exists what are known as very long instruction word or ultra long instruction word architectures, which take this idea even further. All right, especially when it comes to explicitly parallel instructions or instructions that can execute entirely in parallel, essentially. Okay, so so most CPUs that we see nowadays basically have the best of both worlds. Okay, in fact, when we talk about a CPU, we usually talk about a CPU also in terms of the number of bits. All right, that particular CPU has. In the past, we used to talk about a 32-bit computer. Now we're talking more predominantly about 64-bit computers. Essentially, that in essentially that tells us um, uh, how many bits a core can process at any given point in time. All right. So a long instruction word could actually make use of multiple cores working at the same time. For example, say you have 4 cores, all right? So you would take 64 times 4, all right? And that would be your entire um, uh, instruction set, all right? So 1/4 of it would go to one core, another fourth of it would go to another core, and so on and so forth. All right, but obviously that would predominantly require the compiler to to create these instructions in such a way that make it as efficient as possible for the CPU in order to run this. However, this is not easier said than done. All right, why? Because every computer has essentially different instruction sets. All right. If you have an AMD processor versus an Intel processor, you have different instruction sets. If you're using an Apple device or a Mac device versus an Intel or AMD processor used on Windows systems, you probably have a different instruction set. All right. If you're using a mobile phone, all right, you have a different instruction set altogether. So each architecture, even different generations of CPU, and even from the same company, have different instruction sets. All right, even different models, all right, might have different instruction sets. So you can imagine how complicated the work could be for a compiler in order to convert programming instructions into the ones and zeros that the CPU can actually understand. Are there any questions so far? Yeah, yes. Essentially, you'd have the circuitry for both. All right, on the same chip. Nowadays, obviously, with smaller and smaller chipset size, you can actually fit more and more of these types of circuits on your CPU, therefore making it able to calculate more of these different types of instruction sets. Essentially, that is one of the reasons why AMD has taken such a big leap forward recently, because they came up with the 7 nanometer architecture versus the 14, if I'm not mistaken, of Intel. I mean, even I think, was it 14 or 10?
I think they went down to 10 now, but they were
went
on 14 for a very long time and they lost ground.
exactly. So one of the reasons why AMD has caught up so much is because it can actually do more of these kinds of operations, because you can actually fit more on the same chip. Essentially, in terms of size, they're relatively the same size.
So the decision for which circuitry runs particular instructions, this falls down to the compiler now with these kind of architectures.
So first and foremost, the whenever you install a compiler on a computer, so essentially what you do is um, uh, you are installing a compiler on a machine, which basically means that the compiler is now aware of the type of instruction sets that the CPU can operate.
Mm-hmm.
Okay, so it will have that list in its mind. Then, when you compile a program, whatever that program happens to be, all right, the compiler will try to convert the instructions that you have written in your program, all right, into instructions that that particular machine would be able to understand.
Mm-hmm.
All right, based upon the instruction set that it can cater for. All right.
Okay.
Now, obviously, the way that conversion actually happens, all right, that is really and truly down to the compiler itself. And a compiler is a program, really and truly, like any other program. It can be written more efficiently than others, or less efficiently than others. So the quality of the conversion is going to be down to the compiler itself in this case.
All right. So you can technically have cases where it forwards the wrong instructions, for example.
No. If you have a good compiler, then you would always get the same sort of like execution. However, what might happen is that with different architecture, with a different hardware setup, all right, the same program might run more efficiently on one machine versus another.
All right.
Okay, that's
Okay.
essentially the idea. All right, even if you have the same sort of like specifications underneath, for a particular problem or for a particular program, it might run more efficiently on one system than it might run on a different system.
All
That's
right.
essentially.
Understood. Okay.
Okay.
Thank you.
All right. Yes. 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 This is also why. This is also why. Um, uh, it, it's only been relatively recently that programs were able to be written on different machines and written on one machine and executed on another. In fact, in the past, when you came up with when you wrote programs for particular computers, you wrote them natively to the computer that they were actually going to execute on. All right. But then what we introduced was the idea of virtual machines. All right. In fact, Java has a virtual machine. Essentially, um, uh, all of the programming languages that are provided by Microsoft use the .NET framework, which underneath essentially is a virtual machine. All right. Essentially, what is a virtual machine? A virtual machine is an interface, if you will, between what the program thinks your computer is like versus what your computer actually is like. All right. So the virtual machine sort of like provides a similar sort of like platform. All right, for each and every application of that particular programming language. So if we're talking about a Java application, we're talking about the Java virtual machine. The Java virtual machine is the same essentially on each and every machine that has Java installed on it. However, it interfaces um, uh, with the computer in different ways depending on the architecture that you have. That's why you can have applications, all right, written in Java on a Windows system that can run on Mac, that can run on Android, that can run on, because you have this element of virtual machine. Obviously, it's not as efficient. Okay. Okay, so that is essentially what I had for you with regards to the idea of pipelining. The next topic that I wanted to put forward to you is this, which has to do more with instruction sets. Okay, this particular unit that we're going to be talking about over here is very, very important towards your assignment. Okay, in fact, in the next lesson that we're going to have together, I will be explaining your assignment, all right, which has to do with the idea of the instruction set. Okay, so essentially, what we're going to be understanding is what makes up an instruction set, all right. We're going to look at definitions of what we know as being what is an opcode, what is an operand, all right, and we're going to be looking at very simple programs in assembly, all right, so that we can understand how the computer can actually understand what needs to be done, all right. As we said, all right, every machine, all right, has every computer, every CPU has a number of different functions that it can actually operate. All right, if you think about it, all right, an instruction set is basically the processes that that particular machine can actually operate. If we talk about it in terms of a DVD player, all right, the DVD player can stop, play, fast forward, rewind, and so on and so forth. All right. And these are all different functions that the DVD player can actually do. And obviously, the way that these instructions are carried out depend entirely on what button the user is pressing on the remote. In a very similar fashion, all right, the CPU can perform a number of different operations, being it arithmetic, be it data manipulation, all right, bit manipulation, and so on and so forth, all right, based upon instructions that are given to the computer via instructions from our code. So essentially, we need to first and foremost understand the complete set of instructions that are going to be recognized by the CPU. That set, all right, is known as the instruction set. All right, and as we said, instruction sets can vary from a few dozen to a few hundreds or a few thousands, all right, depending on whether or not you fit on the RISC side or the CISC side, all right. Usually, these forms of operations fall under a number of different categories. One is arithmetic and logical processing, essentially where you'd be able to conduct addition, complementation, so negation of twos, complement numbers, all right? Maybe you want to be able to do comparisons, subtractions, multiplications, and divisions, and so on and so forth. And maybe not only just for integers, but also for floating point numbers. Most modern CPUs also have floating point processors instead of just ALUs, all right? They have FPUs, all right? As well as other operations such as bitwise operations, all right? So left shift and right shift, all right? As well as gate logic, all right? So and, or, not, and so on and so forth. You also have other forms of instructions which are known as control transfer instructions. These are the instructions which execute specific portions of other instructions based upon certain situations, all right, within the code itself. They're usually controlled through the use of flags. So essentially, once certain flags are triggered, all right, within the status register, the CPU would know what it would need to do in relation to the rest of the application, all right, based upon those executions. So, for example, the CPU might say, listen, I am going to now continue executing from address location 1000 if the 0 flag is set. Notice it's not just a one flag trigger, it could also be multiple flag triggering a certain event. Okay? Another form of instruction class is known as data transfer. Essentially, this is when the CPU is trying to move data between memory, all right, and its registers and vice versa, all right, and maybe even to other peripherals on that are attached to the main board, all right, as well as input and output, all right. So essentially, when the computer is going to be reading and writing to these I/O devices, okay. Now, when we talk about an instruction being executed, essentially what we're talking about is the instruction cycle, all right? Normally, all right, it's simplified to the fetch, decode, execute cycle, or sometimes also known as the fetch, execute cycle. Essentially, the CPU needs to follow a number of different steps, all right, which in our previous section we called a pipeline, all right, in order to calculate an instruction, the outcome of a particular instruction, all right. Now there are going to be a number of different steps. Usually, all right, they fall under these 5 categories. So first, we fetch the instruction. Essentially, what we're doing here is we're reading the instruction from memory, all right, specified by the program counter, all right, and we copy that instruction into the instruction register. All right. Once we have that copy within the instruction register, we decode the instruction. We try to understand what data, if any, is required, and we retrieve that from memory. All right. Once we've decoded our instruction, so we know what we're going to do, and we know upon which data we're actually going to apply that instruction or that operation, we then update our program counter. Now, our program counter is essentially going to now point to the next instruction within the sequence. Usually, what we do is we take the length, all right, of the instruction that we've just read, and we add it to the address of the program counter that we've just read, all right. Then we execute the instruction, all right. So we perform the operations by triggering the correct circuits in order for that particular operation to be fulfilled, and then go to the end of the cycle, which in turn reaches back up to the top. Now, as you can see, there are a number of different stages, all right, that we're talking about this fetch execute cycle, which happen inside the CPU to a certain extent and outside of the CPU to another extent. So if we had to look at it in a more visual manner, all right, you would see that first and foremost we calculate the instruction that we need to execute. We then fetch the instruction. Notice that we're fetching the instruction from memory, all right, and we retrieve it and store it within our instruction register, in which case we start to decode the instruction. By decoding the instruction, we're going to be calculating what operands, all right, what data we're going to be working with, all right. Sometimes you need to fetch multiple operands, all right. Once you've fetched all of the operands, then you perform your operation. You perform your calculation. All right. You calculate where you're actually going to be storing that value, and you might be writing that value or multiple values, all right, to memory. All right. And once you've done that, you calculate the next instruction. This is essentially a state machine diagram, which showcases, all right, at which stage you're actually communicating with main memory, and at which point you're actually working within the CPU, essentially. Any questions up to this point?
All clear.
Okay. So, usually when we talk about an instruction usually has a predefined length, all right, or has a variance length, but their size is always an integral number of bytes or words. What do we mean by this? The shortest instruction that you can actually have is going to be 1 byte, okay, or 1 word. All right. Remember when we talked about words? All right. Usually, when we talk about the 32-bit computer, we're talking about the 32-bit word. If we're talking about a 64-bit computer, we're talking about a 64-bit word. Okay. In the past, all right, the older computers, we also had 8-bit machines, 16-bit machines, all right, and so on and so forth. All right. If you remember the Amigas, for example, those were 8-bit computers, and then they became 16-bit computers, and so on and so forth. All right. So essentially, what they could handle was different sized words. Right. Now, in some CPUs, all right, the instruction is always going to be the same size. All right, no matter on whether or not that size is required, really and truly. Maybe some instructions will only make use of a third or less of the instruction size in its totality. All right. This idea is used because it simplifies the fetch decode execute cycle. So essentially, it simplifies how you're actually going to be looking for the next instruction, because you're always going to look for the next instruction, which is so many bits further away, or so many bytes further away from your previous instruction. All right. However, it also means that you're going to be a bit more wasteful in terms of space. Okay. On the other hand, where you have CPUs which cannot actually afford this wastage, what they might have is variable length instruction sets. All right. So different instructions might vary in length. All right. But obviously that means it complicates the fetch execute cycle. All right. So it's either one or the other. All right. And each instruction is usually made up of a number of different parts. Okay. And each part has a number of bits reserved for that in order to identify what that instruction is all about. All right. So let's take a look at a typical instruction and what an instruction actually includes within itself. So usually an instruction is made up of a number of bits reserved for what is known as the opcode, or rather the operation that needs to be performed. All right. A number of bits which are reserved for the addressing mode that is going to be used in order to interpret the operands. Sometimes it can also be part of the opcode. However, the way that we're going to be looking at it is that it's separate. All right, and then you have your operands. Your operands are essentially the values or the data that you're actually going to perform your calculations upon. All right. So these are the three different elements that make up any instruction. Okay. So let's start off by understanding what the opcode is. The opcode, as I said, is the code associated with each and every different function that the CPU can actually perform. So you have one opcode for addition, another opcode for subtraction, another opcode for multiplication, division, and so on and so forth. All right. So for each and every one of those operations, the CPU is going to reserve a particular operation code or opcode. Okay. Now, the number of bits that you use in order to define the opcode is going to determine the number of operations that particular CPU can perform. So, if we're saying that we're going to be making use of, say, 6 bits, all right, or we're going to have a 6-bit opcode, then our CPU can perform 64 different operations. So far, so good.
Yes.
Okay. Now, when we talk about the addressing mode essentially is used in order to identify, all right, how we're going to be interpreting, all right, the bits for the operand. Okay, essentially it indicates to the CPU the type of data that we're going to be reading, all right, from the rest of the instruction. All right, this is known as the addressing mode. All right, now in our case, all right, it could be the case that we have instructions which take absolutely no operands. All right, so we might say, Ismail, the value of 0 represents those instructions that do not take any operands. All right. So, for example, an operation that wouldn't take operands would be, for example, halt. All right, stop. All right, stop execution. Stop execution doesn't actually require any additional data in order for it to execute. So such an instruction might possibly also have an indication that it doesn't have any more operation or any more to that particular instruction. All right. Another another addressing mode that could be used is to take the perspective that the operands that are actually going to be forwarded to you are the actual data that we're actually going to be making use of. All right, meaning that if the instruction set is saying, listen, the operand that I'm actually passing to you is actual data, and I pass it the value of 5, then it means that I am going to use the value 5 within my calculation for whatever reason. However, we could also interpret that value rather than as data. We can interpret that value as an address, as a memory address. So rather than say, I am going to be using the value 5, all right, I am going to be using the value stored in memory location 5. Okay, so that is the difference. So sometimes we might need to differentiate whether or not we are going to be talking about an immediate addressing or a direct addressing, as we're going to be seeing. All right, in fact, immediate addressing, essentially, as we're going to be seeing in a moment, means that the value that I'm actually going to pass to you right now as an operand is the actual data that you're going to be using. Direct addressing, on the other hand, all right, means that the data that I'm passing to you actually refers to a memory address. Any questions so far?
Okay.
All right. So let's assume that in our simplified CPU, all right, we have a single general purpose register, all right, which is going to be a 16-bit register, all right, which we're going to call the accumulator, all right. In very old machines, all right, you would have this accumulator, all right. The accumulator essentially is a register that holds the data that is currently being executed upon. Essentially, all the numbers that you're going to be adding, all right, are going to be adding directly to the accumulator. If you're going to subtract, you're going to subtract from the accumulator, and so on and so forth. So essentially, with the use of an accumulator, if you want to perform addition, really and truly, you don't need to pass two values. All right, I'm not going to be adding this number with this number, or what I'm really going to be doing, I'm going to be adding this number to the accumulator that I already have. All right, I'm going to be subtracting this number from the accumulator that I already have. I'm going to be multiplying this number with the value that I have within my accumulator, and so on and so forth. Is this clear?
Yes.
All right, so essentially what we're going to have is a CPU which kind of looks like this. Notice that we don't have a number of different general purpose registers, we just have one, all right, being our accumulator, okay? Right, as I talked about when we talk about addressing modes, all right, there are different modes that can actually be used, all right? In our case, all right, our instruction is going to be made up of 6 bits for our opcode, all right, meaning we're going to have 64 different possible operations that our CPU can actually perform. We're going to be reserving 2 bits, all right, for our addressing mode, all right, and we're going to be using the other 8 bits, all right, for our operand, okay? So, or rather, the other 16 bits, sorry, for our operand, okay? So essentially, we have 8 bits for our opcode and addressing mode, and 16 bits for our operand. Okay? So in total, our instruction might be 1 byte long, all right, or 3 bytes long, depending on obviously the type of instruction that we're talking about. So essentially, this is what it's going to look like. All right. So we have our first 8 bits, 6 of which are going to be used for our operation code. 2 bits are going to be used for our addressing mode, and these next 2 bytes are going to be used in order to specify our operand. Notice, all right, notice that our program counter needs only point to the byte, all right, which stores our opcode. So if essentially, whenever we want, let's say we have an instruction which is this long, okay. If we want to go to the next instruction, our program counter needs to be incremented by 3, all right, because this is the first byte, all right, of the program counter. This is the second byte, and this is the third byte. To go to the next instruction, you need to go to the third byte, all right, plus 3. Does this make sense?
Not exactly. Can you repeat that last part, please?
Yep.
So essentially, what we're saying is that the program counter will only point to the byte, all right, which contains our opcode within it. Okay, it doesn't need to point to the entire instruction. It's just going to point to the portion of the instruction which contains the actual instruction. However, our instruction is not just our opcode and our addressing mode. It also needs to include the operands sometimes. Yes?
Yes, fair enough.
So if I have an instruction, all right, which also has an operand, then in order for me to point to the next instruction, I need to refer to 3 bytes away from the current program counter pointer.
Right, all right.
That's all I'm saying.
Okay.
Is this clear to the rest?
Yes, better.
Okay. Yes?
So each instruction is like 3 bits long, right?
In this case, it can be either 3 bits long or 1 bit long. So rather 3 bytes long or 1 byte long.
All right.
Right.
So if it's only one, for the next instruction, it will go to the fourth one.
No, for the next instruction, it will go. If it's only 1 byte long, the instruction is only 1 byte long, then I can go to the next one
Okay.
like this. All right.
All right.
Normally, memory is stored in 8-bit chunks. All right.
Okay.
So
All right.
byte. All right. But if my instruction in this case also has an operand, then I would need to jump to the next stage, to the next instruction, by bypassing essentially our operand. Understand?
Okay. Thank you.
Okay. So, right. So let's take a look, all right, at a fictitious set of instructions that can actually be understood by our CPU. Okay. I say fictitious because essentially what each opcode means is entirely dependent upon, obviously, the structure of the CPU. All right. Since we don't actually have the physical CPU over here, we're coming up with this fictional list of instructions. Okay. So let's say that when we have an opcode with 6 zeros, that means that we're going to halt the program. Does it take an operand? No. Okay. If my opcode is 5 zeros followed by a 1, or rather has the value of 1, that means that I'm going to increment the value of my accumulator by 1. Again, it doesn't need an operand. All right. When the value of my opcode is 2, all right, or 4 zeros, 1 followed by a 0, then it means I'm going to decrement my accumulator by 1. And also that doesn't take a value. All right. When my value of my opcode is 3, all right, then essentially what I'm going to do is I'm going to complement my accumulator. Essentially, I'm going to negate it. All right. And again, that doesn't need an operand. Okay. When my opcode is 4, all right, then essentially I'm going to add the value that I have within my operand, all right, to that of the accumulator. And yes, I would need an operand. Okay. And so on and so forth. 5 in this case means loads the value that I have within my operand into my accumulator. And yes, it takes an operand. All right. 6 stores the value of the accumulator into memory. And yes, it also takes an operand because it needs to tell us where we're actually going to be storing, and so on and so forth. Notice that you don't necessarily need to have each and every operation code filled up with something. All right. In our case, this is a sample set of the instructions that we have. Okay. 7, for example, transfers execution to a different address. So essentially, we're going to continue executing from the next instruction specified by a particular address, and that is going to need an operand. All right. The value 8 will transfer execution of to a specified address if the 0 flag is set to true. And again, that is going to need an operand. The value 9, all right, is going to transfer execution to an instruction specified by the address if the sign flag is set to true. All right. And finally, the value 10 is going to compare the contents of the accumulator with the operand, setting the 0 flag if the two are equal and the sign flag if the operand is bigger than the accumulator. In other words, if the 0 flag is set to true, then whatever you have in your accumulator is equal to your operand, and the sign flag is set to true if the accumulator is smaller than your operand. And again, you're going to require an operand. So as you can see, these codes are going to be the codes that we're going to be using in order to tell our computer what to do. Okay? However, you would probably understand that looking or coding computers using such opcodes can become very, very tedious very, very, very quickly. Okay? So that is why we use what are known as mnemonics. All right, mnemonics are essentially very short, very short abbreviations of the operation codes that we have, which are going to make our lives as programmers easier in order to be able to write our code. So essentially, what we're going to be doing is we're going to be creating a mnemonic in order to represent our operation code. This is the most basic form of conversion. So HLT means 6 zeros. Inc means 5 zeros followed by a 1. Dec means 4 zeros, 1 followed by a 0, and so on and so forth. These here are a 1:1 relationship with the operation code. Essentially, the operation codes that we have over here, that is our machine code, all right? Whereas this mnemonic is part of our assembly code. All right, this is our first programming language, essentially. All right, the most basic form of programming languages. Is this clear so far? This one? Because I am going to be comparing my accumulator with whatever I have within my operand. Okay, that's essentially it. So far, so good, guys.
Yep.
All right. Mana, I'm going to stop here for today. Okay, and I'm going to continue next lesson. What I would suggest that you do is I would like you to take a look at these slides. All right, so that when we come to the next lesson, I will be able to explain a bit faster. Obviously, I will go over what we had discussed in today's lesson in order to help you understand. Right? We're then going to try to execute a simple program together. All right, and then I will be discussing what your assignment is going to be all about because it's very very similar to this. Okay.
Okay, got it.
Okay.
All
Thank you,
right.
Selma. And
Alright.
have a nice evening.
Thank
You
you,
too.
and thank you, Sam.
Thank you.
Thank you.
Bye bye.
Thanks.
Don't forget to
Bye.
punch out.
Yes, thank you.